So we've prepared 4 different pendula. We were careful and made them all the same mass. They're all 500 gram masses, carefully prepared. But in fact, that doesn't matter. The expression for calculating the period is t in seconds, and 1 period is 1 swing out and back to the starting point. That's 1 period. The formula is t equals 2 pi, that's just a number, pi is a number, times the square root of L, the length of the pendulum, divided by g, the acceleration due to gravity. So there's no m anywhere in that expression. So we know that the mass actually doesn't matter. What does matter is that we're assuming that it's an ideal pendulum. An ideal pendulum has 0 mass in the string, all the mass in a single geometric point at the very end. Now they're not completely ideal because these things have some volume. This string has some mass, not very much relative to the bob, but we can assume that they behave like an ideal pendulum. The other thing that's worth talking about is that that formula is an approximation. That formula works very accurately if the swing angle is less than about 10 degrees. So if you're doing this experiment, do that much swing angle. Don't do this much swing angle, because the formula will no longer be really accurate. So small swings. The other thing that's not in the formula is theta, the angle at all. So weirdly and kind of counterintuitively as it might seem, this much swing that it's doing now is the same period, the same amount of time as this much swing. It just travels faster when it travels further. So it's only dependent on the length. And you can see that if we get the different pendula working, that the periods will be different based on the different lengths. You can see that the shorter the length, the shorter the period. You can see the little red guy is swinging much faster, doing many more repeats than the blue or either of the greens. So hopefully that gives you a sense of what's going on with pendulums. And it's also giving you a sense, I hope, of how the formulae are meaningful in physics and how we make that clear to the students. If we get them to say, well, I'm going to do the experiment and I need a balance, please, so that I can check the mass of the bob, you can say, look, have a look at the formula. Do you see an m anywhere in that? No, the mass is not relevant. The mass doesn't matter. So we're actually going to determine the value of g, the acceleration due to gravity, and there's 2 variables. One is t, the period, so I will need my handy-dandy stopwatch to time it, or most of your phones will have a stopwatch on them now, so stopwatches are pretty easy to come by, and L, the length. So I'm going to use a meter ruler to measure it. And we'll use this one. We'll use a longer pendulum to do the experiment because the period is longer, and that makes it easier to be accurate. So to measure the length, I'm going to go from the swing point, so not from up the top here or something, from the place where it's swinging, to the center of mass of the ball, which is not so easy to estimate for something this size. I'm going to say 97.5. So 0.975 meter, we should work in proper SI units. So 0.975 meter is the length of this particular pendulum. And I can work out the period, and then from those I can calculate the value of g. Now we know the value already. We know the answer of this experiment before we do it. It's 9.81 or 9.82. It's in that area. So the experiment really is about how accurate you can be. How good is your experiment? How close do you get to that known value? So in this case, you want also to calculate the uncertainties. So I said 97.5, but it might be 97.3, it might be 97.7. So I'm going to write that down as 0.975 plus or minus 0.2. That's centimetres, make that 2 decimal places further back for meters. So plus or minus 0.002. And then I'm just going to time it. Now, to time it, I'm going to swing it less than 10 degrees. I'm going to not start timing. It's very tempting to just go, all right, particularly if you have a group, to say, all right, you let go, I'll start the clock. But that means you've got the reaction times of 2 people involved. And most of us are not Grand Prix drivers or MotoGP riders. We don't have super, super good reflexes. Our reflexes are off by maybe 200 millisecond, 0.2 of a second. So the more humans you get involved, the less accurate your result's going to be. So what I'm going to do is get it swinging first and then start timing from a particular swing. I'm going to swing it, time it for multiple swings rather than one swing, because that kind of submerges the human error. If the period of this is around about 2 seconds, I think, I'll check it in a second, a 1 meter pendulum has a period of roughly about 2 seconds. So the amount of swings that I take where I'm not messing with it, where there's no human involved, kind of submerges the human error at the end, if that makes sense. So I'm going to get it swinging, I'm going to time it for 20 swings and then divide by 20 to get the time for one swing. I'm going to time it from the top of the swing, not from the middle, because it stops at the top of the swing and it's moving its fastest at the middle. So it makes sense to do that as well. I'm talking about these things about how you make your experiment as accurate as you possibly can. So let's do that. So I'm going to start at 0. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And it's 39.93 seconds. So I did say earlier that the period for one swing would be about 2 seconds. We did 20 swings and it was very, very close to 40 seconds. So I was right. This is always encouraging. So I'll write that down, 39.93 seconds. What's my uncertainty on that number? Probably pretty small. We're timing down to hundredths of a second. So our uncertainties are going to be something like half that. So it'll be 39.93 seconds plus or minus 0.005 seconds. That's probably overstating our accuracy because, as I said, humans are accurate to within plus or minus 0.2 of a second. So you could actually say 39.93 plus or minus 0.2, which is actually quite a big error bar, but it's probably more accurate, I think, in terms of calculating that uncertainty. So hopefully we're using those two data points. Now, again, I'm not just going to do it once. I'm going to do my experiment at least 3 times, probably 5 times, and average my results, because that also helps to submerge the errors. If I was a little bit slow this time or messed up something a little bit, then it means that averaging multiple measurements will kind of submerge those errors in particular trials. But you should end up with an answer around about 2 seconds. You know your length, you know the period, and you can calculate from that the value of G and make sure that you actually include an estimate of the uncertainty of your value of G. So it might be 9.82 plus or minus 0.2 of a meter per second squared as a value of G. But you need to be able to state and justify why you think you know it to within that level of certainty. This is the determination of the value of G, the acceleration due to gravity. And as I think I mentioned in the lab video, we know the answer. The answer is about 9.81 meters per second squared. But we're trying mainly in this experiment to see whether our experimental procedure was good and accurate. So you can see on the table there some data I prepared earlier. So basically lengths versus 20t, which is 20 times the period, the swing counted for 20, because counting for 20 rather than for 1 makes it more accurate. And then just that number divided by 20 gives you the actual t, the period. And I think I said in the video, at around about a meter, the period is around about 2 seconds. And then for reasons that will become obvious in a moment, we have a column for t squared. So let's just quickly work through the setup of this problem. We have an expression which is t equals 2 pi times the square root of L over G. That's the expression for the period of a pendulum. It has a couple of assumptions in it that theta is small, that the angle of swing is less than about 10 degrees, is kind of implicit in that formula. So if the swing is larger than that, and again, I think I may have mentioned this in the lab, it will be less accurate. So we kept our swings small. You can see the mass isn't a variable, and well, the angle isn't a variable. As I say, we keep the angle small for that reason, that this is really an approximate formula rather than a precise formula. Now, what we want to do is have G as the subject, because we're trying to determine the value of G, so we need to do a little bit of algebra. So I'm going to square everything because I'm not a big fan of square root signs. So if I square t, I get t squared. You might be starting to realize where this column comes from. If I square 2, I get 4. If I square pi, I get pi squared. Remember, that's just a number. If I square root of L over G, I just get L over G. And this is a valid move. You might think about squaring the bits and pieces, but as long as it's a multiplication, not an addition, it still works overall if you square each of the bits of each side. Now, I'm going to multiply both sides by G because I want that as the subject. I'm going to do this in slow steps so that it's all very clear and explicit what we've done and why. And then divide both sides by t squared. So G equals 4 pi squared, and I'm going to write it as L over t squared. Now, 4 pi squared is just a number. Pi is about 3, pi squared is close to 10, 4 pi squared is close to 40. So we're going to multiply this, L over t squared, by 4 pi squared, and that will give us our value of G. So the answer we get for L over t squared is not in itself our value of G. Now, as we could have done for the specific heat, we could just calculate L over t squared. We've got L at that end of the table, t squared there, put it here, do those calculations and average them. But as we did in that case, we're instead going to do a graph because it's more accurate. Now, we need to think a little bit about our uncertainties. For the distance, it's relatively simple. This is basically 0.9, so that's 9. These are meters, so that's 97.5 centimeters. So our smallest unit that we're using is centimeter, so our uncertainty is going to be half a centimeter. So it's going to be 0.0005 meter. That's going to be the uncertainty in the length. So that's fairly precise, and that's okay. Our time, typically human reaction time, and I'm again no motorcycle racer or whatever, typically human reaction time is on the order of 0.2 of a second, 200 milliseconds. So I'm just going to use that value as plus or minus 0.2 of a second. So you can see that the imprecision, if it's there, comes in the time rather than coming in the distance, the length, because we can measure it less precisely because our reflexes and our skills in measuring it are hard. And we were doing a lot of it by eye, just looking at where the pendulum swings to. So there's a margin of error there. Now, when we square something, we don't square the uncertainty because that would make the uncertainty smaller, which doesn't make sense. If you square 0.2, you get 0.04. So that's unhelpful for our purposes. So what we actually do is going to look at the proportional uncertainty. So essentially we've got about 0.2 in 2, so that's about a 10% uncertainty. So what we'll do is just have about a 10% uncertainty in each of these. So, and because it's proportional, it's going to be on the order of plus or minus 0.4 there, it's going to be different. And that means the error bars will be slightly different lengths as we get shorter and shorter. You'll also notice that I decreased the length of the pendulum. I started with a long one and got to shorter and shorter ones. That's because the periods get shorter and shorter as the pendulums get shorter, and it's easier to time. So I kind of got my hand in on the easier ones and then did the harder ones. That's going to be plus or minus 0.3 approximately. That's going to be plus or minus 0.3 also, because if you take that to the right number of sig figs, plus or minus 0.2 and plus or minus, probably technically should be 0.2 as well, because that rounds to 2. So now we can draw our graph. So on our graph, what we want is that the gradient will be L over T squared. So I maybe didn't make it as explicit as I should have on the specific heat one, but when we get the gradient of a line, what we actually calculate to get the gradient M is the rise over run, the vertical over the horizontal. So that means you end up doing the y-axis divided by the x-axis. So in this case, we will have a number of values of L. You'll kind of put them in the reverse order to that, I guess. If you like to put your data points upward, you'll put your data points in, you'll put your vertical error bars in, and these are the ones we're using. We tend not to use horizontal error bars, although we do have these uncertainties in the time of the thing. So we could notionally do horizontal error bars as well, and they're actually going to be bigger than the vertical ones in this case. The vertical ones will be quite small, although we're really only going from 0 to 1 in terms of length. We get to almost 1 meter. And we're going from I guess probably 0 to about 4, maybe 4.5 second squared. So the units of t squared have to be seconds squared, not seconds. The units of L are meters, they're distances. So you'll draw your, put your points in, you'll put your vertical error bars in. As I say, don't worry about horizontal ones for the purposes of this. And as you did for the enthalpy, you will create your maximum slope line and your minimum slope line and your best slope line and report all of those. And then you'll tell us whether your result is within those errors of the known value 9.81. So you'll have a number for the value of G. You'll take this gradient from that M, and multiply that by 4 pi squared, and that will give you a value of G. Now, whatever your value of G is, you will then compare it to the known value from the literature, again, as we did in the specific heat, and be able to actually make a judgment about whether you think that, or how accurate you think the experiment was. And also maybe some conversation about whether you think the error bars were big enough. If your value is not within the uncertainty, if the real value is not within the uncertainty from your experimental value, then perhaps your uncertainties are not big enough to take in the real value. Hope that makes sense.